So, in this session, we will be working on a very important topic from both knowledge perspective and from your VTU examination perspective. Okay, because this question will be 100% sure. Okay, so we'll be having three bits in this phasor diagram, which you have to develop it for a resistive load, inductive load, and capacitive load. So out of three, any one concept will be 100% will be asked a sure short question, I can say, on this topic. Okay, so you have to give a lot of concentration on this particular topic. Okay, so in this session, we'll be working on a topic called as transformer on load. So we're working on a topic called as a transformer on a load. Transformer on load. Okay. So now I will develop a circuit, or I can say that a circuit which uh, resembles a practical transformer. So, wherein the previous sessions we have talked on how can I define the term practical transformer. So, let me say that this is my magnetic core. Let me say that this is my magnetic core. Okay. So, this is the area where it allows my uh, primary power to be transferred onto secondary via the help of the magnetic frame. So I'll be having my primary winding on this limb and a secondary winding on this limb. So as we know that we call this as a primary winding just for a simple reason it is being connected to the source. So this is my input voltage V1, okay, and I call this winding as a secondary winding just for a simple reason this is being connected to a load. Now, as we have said that we are going to develop an circuit which resembles a practical transformer, I know that in case of a practical transformer, I need to consider the effect of windings, saying that so these windings they are going to possess some amount of internal resistance. So that is being shown here, indicating some resistance R1, and the resistance of your secondary winding is being shown over here with R2 in order to resemble the concept of leakage flux because of the leakage reactance. So that is being shown over here with the help of an inductive symbol called as an X1, and the leakage reactance, or the I can say that the concept of the leakage flux seen on the secondary winding is being represented with the help of an inductor on this side indicating an X2. Okay, as we know that whenever a primary voltage is applied, so at that time this circuit is a closed circuit which makes a primary current to flow into this primary winding, which makes some flux to be induced or developed in the primary winding, which links itself. So this is called as a primary leakage flux by L1, and part of the flux moves from the primary and links to the secondary like this. So this flux we are calling it as working flux. So since this EMF is getting induced across this winding because of the flux produced by its own, so this is called as a self-induced EMF. And since one more EMF is getting induced over here, so because of the flux linking from primary to secondary, so this flux we call it as mutually induced EMF. Mutually induced EMF. Okay, and now since the secondary circuit is also closed, then I can simply say that there will be some current in this secondary loop. Let me call that current as the current I2. When this I2 current flows to this load, it creates a voltage drop, so that I call it as a V2, nothing but load voltage or terminal voltage. So my V2 exists across this load. Okay, so this is what I can represent as a concept of my practical transformer on load condition. Okay, so as I know that in my electrical circuit, I'm having three types of loads. I'm having three types of loads. So this load, now at present I've shown it as a black box, okay, as some square box. So this load can be either a resistive load, or it can be an inductive load, or it can be an capacitive load. So what we'll do is we will take the same circuit, iterate it in three different cases. So what happens to my circuit, if at all, if this load is resistive in nature? So we'll make a proper analysis of that. Then we'll remove the resistive load and we'll include the inductive load, and we'll make an analysis that how does the circuit is going to behave. So even I want a feedback that you people are able to understand the topic or not. So for that reason, for that simple reason, I'll give this capacitive load as an assignment to you. So you people need to just remove this inductive load and insert a capacitive load and make a similar analysis as such. Okay, I'll give a sufficient hints to you people to make the proper analysis. Okay, fine. So now what we'll do over here is we'll try to simplify this concept as simple as possible. Okay. So first thing, in order to develop and understand how this circuit is going to behave, the first thing we are going to identify is what is the impedance, what is being seen on the primary side. The impedance that is seen on the primary side is represented as Z1. Okay, as I'm having some amount of the resistance R1 and X1, so I can write my Z1 as simple as R1 plus J times that of X1. Similarly, I would like to know what is the amount of impedance on my secondary side. The impedance on the secondary side is being given by Z2, which is nothing but R2 plus J times that of X2. R2 plus J times that of X2. So now I want to develop an equation to know what is the amount of primary voltage that I'm applying to this transformer. So I want to know what is my primary voltage V1. I want to know this. So in order to know this parameter, what I need to do? I want to know what is my V1. Yes, any suggestions from your side? What best I can take a step over here? I want this voltage V1. I want this voltage V1. Yes, please answer me in the group chat. Okay, so your friends are suggesting ohms law you want to do. So my dear students, I want to know what is the voltage that I have to apply to this circuit. So in order to have that information, I'll be simply employing the KVL in this loop. I'll be employing a simple KVL in this loop. Okay, because now if at all if I start applying this KVL, so let me denote the polarity into the circuit. Now, please concentrate on these polarities. It's very important. Now, let me say that as I know that my input is sinusoidal in nature, so at any time it can be positive, negative, at any time it can be negative, positive. I agree. But I am taking an instance. I am taking an instance. If at all, if I stick on saying that this terminal is at positive potential and this terminal is at negative potential, so keeping my input potentials fixed, keeping my input polarity fixed. Now I would like to make some proper analysis on what is happening onto my input loop. Now since this is positive, this is negative, what is this even? It's an induced EMF. Am I right? It's an induced EMF. So this induced EMF will be having a polarity reverse as that of your supply voltage. Your induced EMF will be having a polarity reverse as that of your supply voltage. It simply indicates now, so this will be negative and this will be your positive. Okay, so this is in accordance with your Lenz's law. This is in accordance with your Lenz's law. So E is equals to minus n d phi by dt. So that equation you are using in order to suffice this polarity. Then next is that now since your input polarity is positive negative, so current is going to go in this direction from negative to positive. So it means this is the amount of impedance what is being seen by your current I1. So when current moves from this node to this node now, what happens? So there exists an voltage drop. There exists an voltage drop. So to indicate that voltage drop, so this will be positive, this will be negative. Understanding? I hope this polarity is clear to you now. I hope this polarity is clear to you, right? So now what I can do over here is, now I'll start writing the equation with the help of these polarities. Okay, so let us apply the KVL at input loop. Let us apply the KVL at input loop. So let us start from the input side. Negative to positive, it is positive. So I'll write this as plus V1. Agreed? Then next, I'm moving from positive to negative. So this is minus. Okay, the current that is flowing into the loop is I1 and the impedance offered together is Z1. So this is togetherly Z1, right? This is togetherly Z1. So I can write this as minus I1 into Z1. Then I'll be getting negative to positive. So positive, what is this? It's an induced EMF E1. So this will be equal to 0. So I want to know what's the equation for V1. So how to get the equation for V1 now? So V1 will be equal to, I'll throw this even from my LHS to RHS. So it becomes minus E1. So I'll send this this term from again LHS to RHS. So it becomes negative becomes positive I1 into Z1. So let me call this as expression 1. This is very, very important. Okay, in many of the books you will get this as this equation directly. Okay, you should not get astonished that how this equation is coming. So you need to simply understand that you applied KVL onto their input side and you are able to get this equation. Okay, then next is now similar such equation I would like to have onto my output loop. Again, very important. Important is how you are denoting the polarities. Now, you need to understand that E2 is also an induced EMF. E2 is also an induced EMF, and E2 will be having the polarity as that of E1. So whatever is the polarity on E1, same will be the polarity on E2. Even you have seen the same in case of a phasor diagram. You represent your E1 and E2 onto the lower y-axis or bottom y-axis. So since this is negative, this is positive, E2 will be having a polarity negative, positive. As I said you, E2 will be having polarity as that of E1. So since this is negative positive, even this also will be negative positive. So whatever is the polarity onto your induced EMF, the same polarity exists onto your load. So it means even your load will be having negative positive. Now one thing that you need to understand over here is onto your secondary loop, your E2 is acting as a source. It's a very important point that you people need to understand, because there is no physical interaction between your actual source and secondary circuit. These two circuits, they are electrically isolated, but they are coupled magnetically. They are coupled magnetically. Am I right? So it means the power source element onto a secondary circuit is your E2. The power source element onto your secondary circuit is your E2. So E2 is a driving element into a circuit, or E2 is an active element into a circuit. Now, since this is negative positive, so it means the current has to flow from negative to positive like this. So it simply says that now when the current starts flowing in this direction, then there occurs a voltage drop. how does that voltage drop occurs? That particular voltage drop occurs such that, so this will be a positive terminal and this will be a negative terminal, because since current is moving, since I is moving in this particular direction, so when it leaves the, I can say the impedance terminal, so there should occur some voltage drop. There should occur some voltage drop. So therefore, so this terminal will be a positive terminal and this will be a negative terminal. Okay. So now if I apply KVL to this particular loop, if I apply some KVL to this particular loop, what's that I'll be getting? So for your reference, I'll just keep this diagram in front of you and develop the KVL so that will not get confused. So we'll apply, so say that let us apply KVL at output loop, What is that we're going to get now? So let me say that I'm moving from negative to positive. Therefore, this is positive. Am I right? So I'm moving from negative to positive. So this is positive. What is this? This is E2. Then I'm moving from positive to negative. So therefore, this is negative. What is that? It is minus V2. Then again, I'm moving from positive to negative. So what is this? So this is negative I2 into Z2. I2 into Z2. So this will be equal to 0. This will be equal to 0. So now I can write this equation so that I can get what is the voltage, what I'm going to get onto my uh, as an induced EMF. So even for the input loop, I was writing the equation for V1, which is a source into my primary circuit. Similarly, I want to write what is my source, what's magnitude of my source onto my secondary. So since E2 is acting as a source, so here I'll be writing an equation for E2. So my E2 will be equal to V2. So I'll just throw it on the side plus I2 into Z2. So E2 will be equal to V2 plus I2 into Z2. So let me call this as equation number 2. Okay. So I hope that you people also remember how you people are going to call as Z1 and Z2. So for your better understanding, I can write this as V1 is equals to minus E1 plus, I'll split this Z1 because I know that my Z1 is R1 plus J times set of X1. So if I take this I1 separate, what I'll be getting? I1 R1 plus J times that of I1 into X1. So this is a very, very important equation which we are going to implement in terms of a phasor. This is very, very important. This you people need to keep it as a reference. Similarly, in case of a second loop, what is that we'll be getting? My E2 will be equal to V2 plus I2 into Z2. What is my Z2? Z2 is R2 plus J times that of X2. So if I take I2 separate to each term, what is that I'll be getting? V2 plus I2 R2 plus J times that of I2 into X2. So again, this expression is very, very important for you when you are developing the phasor diagrams. Okay, so is it clear to you? Then one more thing that you people need to remember, that is you people have to remember this equation. Let me call this as equation number 1. Okay, this equation with the star mark. Okay, and this as my equation number 2. So these two equations will help me a lot in order to build my phasor diagram. Along with this, one more equation that will assist you is the equation for primary current. The equation for a primary current is being given by a summation of a no load current I naught plus the equivalent secondary current. So equivalent secondary current, I am going to denote it as I2 dash. I2 is secondary current. Yes or no? So onto my circuit, I2 is my secondary current. What is I2 dash? So since mathematically I know that I2 is the current which is flowing in the secondary loop, but to what extent the load is driving the current. So if I2 is more, then sure shot my I1 will be more. I hope you are able to understand. A simple reason, a simple example I would like to give. Let me say that you people are driving a two-wheeler, okay? So you are driving a two-wheeler. So you alone are available, and you alone are driving your vehicle. There is no one at your second seat. So at that time, I could say that you are almost on no load. You are able to drive your vehicle at your own pace with not much of weight. Now, let me say that you are having a very best friend of yours who is sufficient person, or I can say that a person who is having tremendous amount of a weight. And if he accumulates you people, or if he accompanies you people on the second seat, then in that case, at what pace you are riding, so that pace may not be enough for you in order to drive ahead. So you have to increase your accelerator. So it means your source, what is there, it should rise up depending upon the load. So I simply mean to say, as you go on increasing this load, the current I2 also increases. Increase in the I2 proportionately makes increase in I1. So this is your accelerator. This is your very good friend who is sitting here. So if the person who is sitting here, so if his weight is more, then naturally I2 will be more. Since I2 is more, you driving the vehicle has to increase the acceleration. Understanding? So this same process I am just letting it to your day-to-day life. Okay. So it means now since I2 is in one circuit, a secondary circuit, I1 is in another circuit. Okay. So but I want to make a proper analysis. To make this proper analysis, I need to transfer my I2 from one circuit to another circuit. So in order to do that, that is what I'm calling it as I2 dash. So wherein it is an equivalent secondary current as seen on primary. Okay, so in our next topic we'll be discussing about something called as equivalent circuit of transformer. So at that time we will surely come across these terms in detail in depth. So let me not drag that topic over here. Instead, let me isolate that topic and just let me say you I2 dash is nothing but an equivalent secondary current, just for an information. So I2 dash is nothing but an secondary equivalent current. So it means my I1 is equal to a no load current plus the secondary equivalent current. So these three equations are very important for you people when you start developing your phasor diagrams. Okay, so now we'll start building the phasor diagram, assuming that the load in our case is a resistive load. Okay, so now we are building this phasor diagram, assuming a case of a resistive load. Assuming a case of a resistive load. Okay. So now we'll consider a case of a resistive load. Yes, prior to starting this phasor diagram, I would like to know that whether you people are able to understand what all the analysis with the help of KVL they are able to do. Whether those statements, those interactions are clear to you. Yes, please answer in the group chat. Yes. Okay. Good. That's good. So now we'll build this phasor diagram. I'll be slow enough. Okay, I'll be slow enough so that we can catch up the all concepts related to this. Okay. So now let me say that. Let me say that. So first, I'll be drawing a parameter which is common to both my primary part as well as a secondary side. So it simply means that I'll be considering my flux phi, which links both the primary circuit and the secondary circuit. Now, let me say that this as my origin. I will be drawing a phasor diagram. Okay, so this phasor is nothing but flux phi, which is a common parameter to my both primary circuit and secondary circuit. Now, in the previous case, when we're drawing a transformer on no load condition, so we said that there are two components. One is I mu. So let me draw it with some other color. that you should not be confused. So one is I mu, wherein we said that this I mu is called as magnetizing current. This current I mu is called as magnetizing current, who is responsible to produce the flux in the circuit. Understanding? And there also exist some magnetic losses because of their magnetic elements. So that magnetic loss you are able to represent with the help of one more current vector, with the help of one more current vector. So that current vector, we just represented it as IW. IW. So if I take the resultant of these two vectors, then this gives me my no load current. This gives me my no load current I naught. This gives me my no load current I naught. Okay, fine. Now I have developed my no load current I naught, where no load current I naught is the vector sum of I mu and I omega or IW, what is that you can call it as. Then next, now I need to compute the phasor for my I1, the primary current. Okay, the phasor for my I1. I know that with respect to phasor equation, what it is saying? It is saying that you can get your current I1, you can get this current I1, provided if you are having the information of your no load current and I2 dash, that is secondary equivalent current. Now, what is that I'll be doing over here is, now I'll build my I2 first so that I can get my I2 dash. So I know that. So if this is the flux phi, where is my E2? E2 is the EMF which is being induced on the secondary side. So my E2 is represented here. So this is my E2. Okay, this is my E2. Then next, now if you see this secondary part of the circuit, when you see the secondary part of the circuit, what is that you're having on the secondary side? On the secondary side, you are having a load which is something resistive in nature. You are having a coil which is nothing but an inductive in nature, and small internal resistance. Do you agree? Yes. Now you need to simply understand that this is representing a simple RL circuit. If you think it from a very broad perspective, this is representing a simple RL circuit. Now since it is representing an RL circuit where E2 being the source voltage, how should be our current? How should be our current? With respect to voltage, whether it should lead or whether it should lag. I repeat, this is your inductive circuit. Okay, I can say RL circuit. Now you are going to consider voltage as reference. And I want to know what's the current relation between your source voltage and your driving current. So in that case, as Savana is saying, we need to have this current I2 such that this current I2 will be lagging. So how is my I2? So I2 will be lagging in nature. So let me say this is my I2. Which is lagging with this source voltage E2. Okay. Now if this is I2, okay, then next, where is my I2 dash? I2 dash simply says that a same vector of the same magnitude projected in opposite direction is being projected in opposite direction. So since this is my I2, how to show my I2 dash? A vector of same magnitude but projected in opposite direction. So this is my I2 dash. So this is something great. Then I'm able to have my I naught as well as I2 dash. What I need to do? I need to just have a vector sum of I naught and I2 dash, which yields me my current I1. So it means now I am having my I naught, I am having my I2 dash. I have to just apply a parallelogram law in order to get the resultant of this. In order to get the resultant of this. So it means this is my current I1. This is my current I1. So when I1 is a vector sum of I0 plus I2 dash. Okay, fine. I hope it's interesting. Okay. So now what we'll do over here is, so we have implemented this expression, that is I1 is equals to I0 plus I2 dash. So now we'll try to implement the equation what we have represented on the primary side. Okay, we'll try to implement onto the primary side. Okay, so now let me say that now in order to get an equation for V1, what all I want the vectors E1, the EMF induced on the primary, a voltage drop I1 into R1, and one more voltage drop J times that of I1 into X1. I do feel we have missed out I1 on the occasion. Okay, so J into I1 into X1. So this is what the details is expected. Okay, so now, so in order to get this minus even, first I need to have my even. So where is my even? So let me assume that this transformer is a step up transformer. So if this is secondary voltage, so where will be my induced primary voltage? So let me say this will be my even, because if E2 is greater than E1, it indicates a step up transformer. It indicates a step up transformer. So if this is even, how will be my minus even? A same vector even has to be projected in an opposite manner, right? So I have to show my even somewhat like this. So this will be my vector minus even. Agreed? So this will be my vector minus even. So I've got this minus even now. Next, what that I need to do? So this minus even has to be added with a voltage drop I1 into R1. Where is your I1? So this is your vector I1. A vector which has been shown in the two lines. So this is your vector I1. Now to indicate this voltage drop I1 R1, what I should do? So R1 is nothing but the resistance offered by the primary winding. Am I right? Now this I1 R1 voltage drop is shown such that that voltage drop has to be parallel to this vector I1. So it means I need to just show it like this. It indicates that this vector is parallel to this vector. Okay, because I know that in case of pure resistive circuit, both current and voltage they will be in phase. Am I right? So there should not be any phase difference between this, because this is indicating a voltage drop across a resistor VR1. So VR1 and your I1 should be both in phase to indicate that this vector should be in parallel to this vector I1, and the magnitude will be equal to the voltage drop across your R1. Okay, so this is indicating, this vector is indicating I1 into R1. Understanding? Now, this as a reference, what I should do now? I need to show a voltage drop I1 into X1. How to show this voltage drop I1 into X1? So since I am having J, so we have studied this in case of single phase circuits. So J is a vector which rotates the original vector by an angle 90 degree. So it means, so this is my I1 R1. So the reactive drop is shown somewhat like this. So with respect to this, this will be 90 degree. So this magnitude is I1 into X1. It's a voltage drop which is seen across the leakage reactance EL1. This is a EL1. So if I take the resultant of this I1 R1 plus I1 JX1, if I take this resultant, What is this? This is nothing but I1 into Z1, the voltage drop which has been seen across the impedance. It's a voltage drop which has been seen across the impedance. So if at all, if I sum up, if I sum up, even if I just sum up this voltage drops, okay, that is minus even plus I1 into Z1. So this should be able to give me, my voltage drop, which is nothing but a V1. So this should be able to give me, my supply voltage a V1. Okay, so this is how we are able to develop the vector even. Okay, so I just quickly repeat it. So first, what you have done, you have taken the reference vector phi, then develop no load current. No load current is defined as the resultant of I mu and I omega. Then you have shown your E2. Since it's a RL circuit, current should lag the voltage. So current is lagging. Current is lagging the voltage. So this is I2. So you want to get your I2 dash. This is your I2 dash. So vector, the resultant vector of I0 and I2 dash is I1. Then you want to write the equation for V1. So what you have done, you have shown first your E1, then minus E1, then added the voltage drop I1 R1 plus J times set of I1 X1. Hence you got I1 Z1. So minus E plus I1 Z1. So if I take its resultant from origin I have drawn a small line. So which reaches this point. So I1 Z1. So minus E plus I1 Z1 is nothing but your supply voltage V1. So this